At the center of distant galaxies, something terrifying is happening. Gigantic black holes, billions of times more massive than our Sun, are feeding on enormous amounts of matter. As gas and stars fall toward these cosmic monsters, unimaginable amounts of energy are released. In some rare cases, this energy forms powerful jets of radiation that shoot across the universe at nearly the speed of light. These objects are known as blazar. They are among the most violent and luminous objects ever discovered. For a brief moment, a single blazar can shine brighter than the entire galaxy that surrounds it. And what makes them even more extraordinary is their direction. The enormous jet of energy they produce is pointed almost directly toward Earth. From billions of light years away, we are looking straight into one of the most powerful cosmic engines in existence, a beam of radiation launched by a supermassive black hole. But this raises a frightening question. What would happen if a blazar existed much closer to us? Tonight, we explore one of the most extreme phenomena in the universe, a cosmic object capable of unleashing unimaginable energy across the cosmos. The mysterious and terrifying power of blazars. The hidden monsters at the center of galaxies, far beyond the stars of our own galaxy scattered across the observable universe, lie some of the most extreme environments known to science. These are not ordinary stars, nor even ordinary galaxies. They are places where gravity, energy, and matter behave in ways that push the limits of our understanding. At the heart of these cosmic environments sits one of the most mysterious objects in existence, a supermassive black hole. Unlike the black holes formed by collapsing stars, supermassive black holes are enormous. Some contain the mass of millions or even billions of suns. Almost every large galaxy we observe appears to host one at its center, including our own Milky Way. Normally, these black holes remain relatively quiet. They sit silently in the dark centers of galaxies, their immense gravity shaping the motion of stars around them. But sometimes, something extraordinary happens. Gas clouds, stars, and interstellar material begin falling toward the black hole. As this material spirals inward, it forms a glowing structure known as an accretion disk, a vast whirlpool of superheated matter spinning around the black hole at incredible speeds. Inside this disk, temperatures can reach millions of degrees. Atoms collide violently. Magnetic fields twist and stretch through the swirling plasma. Enormous amounts of energy are released as matter moves closer and closer to the event horizon. Yet not all of this matter disappears into the black hole. Some of it is redirected. Powerful magnetic fields near the center of the disk channel part of this energy outward, launching enormous beams of particles and radiation into space. These beams, known as relativistic jets, shoot outward from the poles of the black hole at nearly the speed of light. For thousands of light years, sometimes even millions, these jets carve their way through surrounding space. They carry staggering amounts of energy. When astronomers observe galaxies producing these jets, they classify them as active galactic nucleus, or AGN. But within this category exists one of the most extreme types of cosmic objects ever discovered. Objects so bright and powerful that they can outshine entire galaxies. Objects that appear almost impossibly energetic. These objects are known as blazar. What makes blazars unique is not simply their power, it is their orientation. Most active galaxies shoot their jets in directions that do not point toward us. From Earth, we observe them from the side. But in the case of a blazar, the jet happens to be aimed almost directly at Earth. This alignment dramatically changes what we see, because the particles inside the jet are traveling close to the speed of light. The radiation becomes amplified by a phenomenon known as relativistic beaming. This effect causes the jet to appear far brighter than it actually is. The energy becomes concentrated in our direction. To observers on Earth, a distant blazar can appear incredibly luminous, sometimes brighter than all the stars in its host galaxy combined, even though it may be billions of light-years away. Blazars emit radiation across the entire electromagnetic spectrum, from radio waves to visible light, from X-rays to extremely powerful gamma rays. In fact, many of the brightest gamma-ray sources detected by modern space telescopes turn out to be blazars. But brightness is not their only strange feature. Blazars are also incredibly unpredictable. Their brightness can change rapidly, sometimes within hours or even minutes. Astronomers observing them may see sudden bursts of radiation, followed by quiet periods. Then another explosion of energy. These rapid changes suggest that the regions producing the radiation are surprisingly small, perhaps no larger than our solar system, yet they release more energy than entire galaxies. Understanding how such extreme objects function has become one of the most fascinating challenges in astrophysics. How do supermassive black holes produce jets that stretch across millions of light-years? What mechanisms accelerate particles to nearly the speed of light? And why do some galaxies become active while others remain quiet? To answer these questions, astronomers have spent decades studying blazars using telescopes across the world and in space. Each new observation reveals more about the violent processes occurring near supermassive black holes. But the deeper scientists look into these cosmic engines, the more mysterious they appear. Because blazars are not simply powerful, they are among the most energetic phenomena in the entire universe, and their existence hints at forces operating on scales far beyond anything we experience in our everyday lives. To truly understand them, we must explore how black holes, objects once thought to swallow everything, can somehow become the engines that power some of the brightest beacons in the cosmos. The birth of a cosmic jet. To understand how a blazar forms, we must look closer at what happens near a supermassive black hole. Black holes are often described as cosmic vacuum cleaners, swallowing everything that comes too close. But in reality, the process is far more complex. Before matter actually falls into a black hole, it usually begins to orbit around it. Gas clouds, dust, and even entire stars can become trapped by the black hole's gravity. As this material spirals inward, it forms a rapidly spinning disk around the black hole. Astronomers call this structure an accretion disk. Inside this disk, matter moves at extraordinary speeds. Friction between particles heats the gas to incredible temperatures, sometimes millions of degrees. The disk begins to glow intensely, producing enormous amounts of radiation. At this point, the region around the black hole becomes one of the most energetic places in the universe. But the most fascinating part of the process happens near the poles of the black hole. Inside the accretion disk, powerful magnetic fields are constantly forming and twisting. The rotating disk acts almost like a giant cosmic generator. These magnetic fields can become so strong that they begin to channel energy and particles away from the disk. Instead of falling inward, some of the matter is launched outward along the black hole's rotational axis. The result is the formation of enormous beams of energy known as relativistic jets. These jets are among the most extreme structures in the universe. Particles inside them travel at speeds extremely close to the speed of light. They carry radiation, charged particles, and magnetic energy far beyond the host galaxy. In some cases, these jets can stretch millions of light-years across space. That means the jet produced by a single black hole can become larger than the galaxy itself. But not every galaxy with a supermassive black hole produces these jets. Many black holes remain quiet for billions of years. For a galaxy to become active, large amounts of matter must fall toward the central black hole. This often happens during galaxy collisions. When two galaxies pass close to each other, their gravitational forces disturb the gas and dust inside them. Huge streams of material begin falling toward the centers of the galaxies. If enough matter reaches the black hole, the accretion disk becomes extremely bright and energetic. At that moment, the galaxy becomes an active galactic nucleus. Blazars represent one of the most extreme forms of these active galaxies. Their jets are not only powerful, they are pointed almost directly toward Earth. This alignment creates a remarkable effect. Because the particles in the jet are moving at nearly the speed of light, their radiation becomes concentrated along the direction of motion. This effect is called relativistic beaming. It causes the jet to appear far brighter than it would otherwise be. From our perspective on Earth, the blazar appears as an incredibly bright source of radiation, even though the galaxy itself may be billions of light-years away. Modern telescopes have discovered hundreds of blazars scattered across the universe. Some of them are among the most distant objects ever observed. And yet, despite their distance, their energy is so intense that we can detect them clearly. Space telescopes that study gamma rays, the most energetic form of light, often observe sudden flashes from distant blazars. These bursts can release enormous amounts of energy in a short time. In some cases, a blazar can briefly produce more energy than our entire Milky Way. And all of this power originates from a region smaller than our solar system. It is a reminder of just how extreme the universe can be. Black holes, once thought to be silent and invisible, are now known to be capable of powering some of the brightest objects in existence. Through the strange physics of accretion disks, magnetic fields, and relativistic jets, they transform falling matter into colossal beams of energy that travel across the cosmos. But despite decades of research, scientists still struggle to understand exactly how these jets are launched and sustained. Because near the edge of a black hole, the laws of physics operate in ways that are still not fully understood. And somewhere within these violent cosmic engines lies the secret behind the incredible power of blazars, the brightest beacons in the universe. When astronomers first began detecting powerful sources of radiation in the distant universe, many of them appeared almost impossibly bright. Some objects were emitting more energy than entire galaxies. even though they appeared as tiny points of light through telescopes. At first, scientists struggled to understand what they were observing. How could such small objects release so much energy? Over time, astronomers realized that these mysterious sources were not stars at all. Instead, they were distant galaxies whose centers had become extremely active. At the heart of these galaxies sat enormous supermassive black hole, surrounded by swirling disks of superheated gas. These energetic centers became known as active galactic nucleus, or AGN. But among all active galaxies, one type stood out as particularly extreme. These were the objects we now call blazar. Blazars appear incredibly bright not simply because they produce large amounts of energy, but because their energy is directed toward us. The jets launched from the region near the black hole travel at nearly the speed of light. Because of this extreme speed, the radiation emitted by the jet becomes concentrated along the direction of motion. This effect is known as relativistic beaming. It causes the jet's energy to appear amplified to observers located along its path. In other words, when we observe a blazar, we are essentially looking straight down the barrel of one of the most powerful particle accelerators in the universe. This alignment dramatically changes how the galaxy appears to us. Instead of seeing the full structure of the galaxy, we mostly observe the intense radiation produced by the jet itself. This radiation spans the entire electromagnetic spectrum. Blazars emit radio waves that can be detected by giant radio telescopes. They emit visible light that optical telescopes can observe. They emit X-rays that reveal the hottest regions near the black hole. And, perhaps most impressively, they emit extremely energetic gamma rays, the highest energy form of light known to science. Space telescopes designed to detect gamma rays have discovered hundreds of these objects scattered across the observable universe. Some are located billions of light-years away. Yet, despite these vast distances, their energy remains detectable. This makes blazars valuable tools for studying the distant universe. Because their jets are so bright, astronomers can observe them even when their host galaxies are too faint to see clearly. But brightness alone is not what makes blazars so fascinating. They are also incredibly variable. Their brightness can change dramatically over short periods of time. Astronomers monitoring a blazar may observe sudden flares of radiation, followed by periods of relative calm. Sometimes these flares occur within a matter of hours. This rapid variability reveals something important. It suggests that the regions producing the radiation are surprisingly small. In astronomy, the speed at which brightness changes tells scientists something about the size of the source. If an object brightens and dims quickly, it means the region producing that light must also be small. For many blazars, the energy appears to originate from a region only a few times larger than our solar system. Yet that small region is capable of producing more energy than entire galaxies. To put this into perspective, our Sun produces enormous amounts of energy every second. But even the Sun is insignificant compared to the energy output of a powerful blazar. During major flares, a blazar can release energy equivalent to trillions of suns, all powered by matter falling toward a supermassive black hole. Understanding how such tremendous energy can be generated within such a small region has become one of the most important questions in modern astrophysics. Scientists believe that magnetic fields play a crucial role in this process. As matter spirals inward towards the black hole, magnetic fields within the accretion disk become twisted and compressed. These fields may accelerate particles within the jet to extraordinary energies. Once accelerated, these particles interact with surrounding radiation and magnetic fields, producing the powerful emissions we observe. But the exact details remain uncertain. Even with modern telescopes and sophisticated computer simulations, the physics of blazar jets remains an active area of research. Each new observation reveals more complexity. Some jets appear stable for millions of years. Others show sudden bursts of activity. Some jets remain tightly focused across vast distances. Others spread outward into enormous lobes of energy and particles. All of this makes blazars some of the most fascinating objects in the cosmos. They are cosmic lighthouses, shining across billions of light years. They are natural particle accelerators, producing energies far beyond anything humans can create on Earth. And, perhaps most importantly, they provide scientists with a window into the extreme environments surrounding supermassive black holes. By studying blazars, astronomers hope to understand not only how these jets form, but also how black holes interact with the galaxies that surround them. Because despite their enormous power, blazars are not isolated objects. They are deeply connected to the evolution of galaxies themselves, and their violent activity may shape the structure of the universe on the largest scales imaginable. A beam of energy. Across the universe, when astronomers observe a blazar, they are witnessing one of the most extreme alignments in the universe. The enormous jet launched from the region around a supermassive black hole happens to be directed almost straight toward our planet. This orientation is rare. In most active galaxies, the jets extend outward in directions that do not point toward Earth. From our perspective, we observe those jets from the side, allowing us to see their full structure stretching across space. But with blazars, the situation is very different. Because the jet is aimed almost directly at us, the radiation traveling through it becomes strongly amplified by relativistic effects. Particles inside the jet move at speeds extremely close to the speed of light. At such extreme velocities, the radiation they emit becomes compressed in the direction of motion. This phenomenon, known as relativistic beaming, causes the jet to appear far brighter to observers located along its path. To someone observing from Earth, the blazar becomes an incredibly luminous source of energy, even though the galaxy itself may be billions of light years away. This effect also makes blazars appear extremely compact. Instead of seeing the full galaxy clearly, astronomers primarily detect the intense light coming from the jet itself. In many observations, the host galaxy surrounding the blazar is almost invisible compared to the brightness of the jet. The energy produced by these jets is staggering. Particles inside them are accelerated to enormous energies as they travel outward from the black hole. These particles interact with magnetic fields and surrounding radiation, producing a wide range of electromagnetic emissions. Blazars emit radio waves detectable by giant radio telescopes on Earth. They emit visible light that optical observatories can record. They emit X-rays that reveal extremely hot regions near the base of the jet. And, most dramatically, They emit powerful gamma rays, the highest energy form of light known in the universe. Space telescopes designed to detect gamma rays have discovered that many of the brightest gamma ray sources in the sky are actually distant blazars. Even though they lie billions of light years away, their energy is so concentrated that it remains visible across vast cosmic distances. One of the most famous examples is 3C279. This object lies more than 5 billion light years from Earth. Yet, despite this enormous distance, telescopes can detect dramatic changes in its brightness. During certain periods, its energy output becomes so intense that it temporarily rivals the combined light of the entire Milky Way, all produced by a region smaller than our solar system. Another remarkable feature of blazars is how quickly their brightness can change. Astronomers observing these objects sometimes witness sudden bursts of radiation that rise and fall within hours. This rapid variability tells scientists something very important. Because light cannot travel faster than the speed of light, any region producing such rapid changes must be extremely small. If a blazar's brightness changes within a single day, the region responsible for that change cannot be larger than the distance light travels in one day. For objects capable of producing energy on galactic scales, this is astonishing. It means that enormous amounts of energy are being generated inside regions that are tiny compared to the galaxies they inhabit. The true engines of blazars lie very close to the event horizons of supermassive black holes. In these regions, gravity bends space-time dramatically. Magnetic fields become twisted by the rotating accretion disk surrounding the black hole. Particles trapped in these magnetic fields are accelerated to extraordinary speeds. Some scientists believe these jets function as natural particle accelerators, far more powerful than anything built by humans. On Earth, the Large Hadron Collider accelerates particles to extremely high energies to study the fundamental laws of physics. But the jets of blazars accelerate particles to energies millions of times greater. Studying these cosmic accelerators allows astronomers to investigate physical processes that cannot be reproduced in laboratories. Blazars also serve as powerful probes of the universe itself. Because their light travels across billions of light years before reaching Earth, it passes through vast regions of intergalactic space. Along the way, this light interacts with gas clouds, magnetic fields, and faint background radiation left over from the early universe. By analyzing the changes in this light, astronomers can learn about the invisible structures that exist between galaxies. In this way, blazars help scientists explore not only the extreme environments near black holes, but also the large-scale structure of the universe. Yet despite decades of study, many mysteries remain. Scientists still do not fully understand how these jets remain stable across millions of light years. They do not fully understand how particles are accelerated to such extreme energies. And they do not fully understand why some galaxies produce blazars, while others remain quiet. Each new observation raises new questions. But one thing is certain. When we observe a blazar, we are witnessing one of the most powerful phenomena in the universe, a beam of energy launched from the heart of a distant galaxy, traveling across billions of years of cosmic history and arriving at Earth as a signal from one of the universe's most extreme engines. The engines that power blazars At the center of every blazar lies one of the most extreme environments known in the universe. The enormous energy we observe from these objects is not produced by ordinary stars or simple cosmic events. Instead, it comes from a powerful interaction between gravity, matter, and magnetic fields near a supermassive black hole. For many years, scientists believed that black holes were simply cosmic traps, objects that swallowed everything around them and emitted nothing. But modern observations have revealed a much more dynamic picture. When matter begins falling toward a supermassive black hole, it rarely falls directly inward. Instead, it starts orbiting the black hole, forming a rapidly spinning disk of gas and dust known as an accretion disk. This disk is one of the brightest structures in the universe. As matter spirals closer to the black hole, gravitational forces compress and heat it to extraordinary temperatures. Inside the disk, particles move at incredible speeds, colliding violently with each other. These collisions generate enormous amounts of heat and radiation. In some cases, the temperatures in these disks can exceed millions of degrees. The intense radiation produced by the disk alone can make the center of the galaxy shine brighter than billions of stars combined. But the accretion disk is only part of the story. Surrounding the disk are powerful magnetic fields created by the motion of charged particles in the superheated plasma. These magnetic fields behave like twisted springs, storing enormous amounts of energy. As the disk rotates, these magnetic fields become stretched and tangled. Eventually, they channel some of the disk's energy away from the black hole. Instead of falling inward, part of the matter and energy is launched outward along the black hole's rotational poles. This process creates the enormous relativistic jets that define blazars. These jets are incredibly narrow beams of particles and radiation that shoot outward from the center of the galaxy at speeds extremely close to the speed of light. Inside these jets, particles are accelerated to energies that dwarf anything humans have ever produced in laboratories. The exact mechanism responsible for this acceleration is still being studied, but scientists believe magnetic fields play a crucial role. One leading theory suggests that rotating magnetic fields near the black hole act like giant cosmic slingshots. Charged particles caught in these fields are whipped outward at incredible velocities. Another possibility is that shocks within the jet itself accelerate particles as they collide with turbulent regions of plasma. Regardless of the exact mechanism, the result is the same. The jet becomes an enormous beam of energy capable of traveling across vast distances. In some galaxies, these jets extend for millions of light years, far beyond the boundaries of the host galaxy. These jets interact with surrounding gas clouds and intergalactic material, sometimes creating huge glowing structures known as radio lobes. These lobes can become enormous, sometimes larger than the galaxy that produced them. But blazars represent a very special case, because their jets happen to be directed almost exactly toward Earth. We observe them in a completely different way. The radiation produced inside the jet becomes concentrated along its direction of motion through a process known as relativistic beaming. This effect dramatically amplifies the brightness of the jet from our perspective. Even though the galaxy itself may lie billions of light years away, the blazar appears extraordinarily bright. During powerful flares, some blazars release bursts of energy that briefly rival the combined light output of entire galaxies. One remarkable example is Markorian 421, located about 400 million light-years from Earth. Despite this immense distance, telescopes can observe rapid bursts of gamma rays coming from this object. These bursts sometimes rise and fall within a matter of hours. Such rapid changes suggest that the region producing the radiation is incredibly compact. Even though the energy output rivals that of galaxies, it is generated within a region no larger than our solar system. Understanding how such immense power can emerge from such a small region remains one of the greatest challenges in astrophysics. Scientists continue to observe blazars using telescopes that detect radio waves, visible light, X-rays, and gamma rays. By studying these emissions across different wavelengths, researchers can piece together a picture of the processes occurring near the black hole. Each new observation helps refine models of how jets form, how particles are accelerated, and how energy flows through these extreme cosmic engines. But despite decades of study, blazars continue to surprise astronomers. They remain unpredictable. Their brightness fluctuates. Their jets sometimes shift or wobble over time, and occasionally they produce enormous flares that challenge existing theories. All of this makes blazars not only some of the most powerful objects in the universe, but also some of the most mysterious, because within these distant galaxies, hidden behind enormous clouds of energy and radiation, lie the engines that drive some of the brightest and most violent phenomena in the cosmos. When the universe points a weapon at us, among all the strange and powerful objects discovered by astronomers, blazar stands out as one of the most intimidating. Not only because of the enormous energy it produces, but because of its direction. The giant jets produced by a supermassive black hole do not always point randomly across space. Sometimes, by pure cosmic coincidence, one of those jets ends up pointing almost directly toward Earth. When this happens, the galaxy becomes what astronomers call a blazar. From our perspective, we are essentially looking straight into the beam of energy launched from the heart of the galaxy. It is similar to looking directly into the beam of a cosmic lighthouse, except this lighthouse is powered by a black hole millions or billions of times heavier than our Sun. The jet itself contains particles traveling at nearly the speed of light. These particles carry enormous amounts of energy, and when they interact with magnetic fields and radiation around them, they produce intense emissions across the electromagnetic spectrum. Among these emissions are powerful gamma rays, the most energetic form of light known in the universe. Gamma rays are extremely powerful. They can pass through matter much more easily than ordinary light, and in large enough quantities they can damage atoms and molecules. Fortunately, every known blazar lies extremely far away from Earth. Many of them are located billions of light-years from our planet. At such enormous distances, the energy we receive from them is harmless. But the existence of these cosmic beams raises an interesting question. What would happen if a blazar existed much closer to us? To answer this question, scientists have studied the potential effects of extremely energetic cosmic radiation on planetary atmospheres. If a powerful relativistic jet were aimed directly at a nearby planet, it could have dramatic consequences. the intense radiation could strip away parts of the planet's atmosphere. High-energy gamma rays could trigger chemical reactions that destroy protective ozone layers. Without this protection, harmful ultraviolet radiation from nearby stars could reach the planet's surface. Over time, this could make the planet far less hospitable to life. However, the chances of such an event affecting Earth are incredibly small. For a blazar to pose a real threat, several rare conditions would need to occur simultaneously. First, the galaxy producing the blazar would need to be relatively close, within tens of thousands of light years. Second, its jet would need to be pointed almost exactly toward our planet. Third, the jet would need to remain stable long enough for its radiation to reach us. When astronomers examine known blazars, none of them meet these conditions. Most are located millions or billions of light years away. Even the closest known examples are far too distant to affect Earth in any significant way. Still, studying these cosmic beams helps scientists understand the extreme forces operating throughout the universe. Blazars demonstrate how powerful supermassive black holes can become when they actively consume matter. They show how magnetic fields and rotating disks can convert gravitational energy into enormous jets of radiation, and they reveal just how energetic the universe can be. In many ways, blazars represent the most extreme versions of processes that occur throughout the cosmos. Across the universe, black holes shape the evolution of galaxies. Their jets influence the movement of gas and dust. They regulate how stars form in surrounding regions. Blazars simply allow us to observe these processes at their most dramatic, because when the jet of an active galaxy happens to point toward us, we see the full intensity of the cosmic engine behind it. A beam of energy traveling across billions of years of cosmic history. A signal from one of the most powerful structures ever created in the universe, and a reminder that far beyond our quiet corner of the Milky Way, enormous forces are constantly shaping the cosmos in ways we are only beginning to understand. The farthest lights in the universe. One of the most fascinating things about blazar is not just their power, but their distance. Some of the blazars astronomers observe today are located billions of light years away from Earth. This means the light we detect from them began its journey long before our planet even existed. When we look at these objects through telescopes, we are not seeing them as they are today. We are seeing them as they were in the distant past. In astronomy, distance is also time. Because light takes time to travel across space, every observation of the universe is actually a glimpse into cosmic history. For example, our nearest star, the Sun, is about 8 light minutes away. When we look at the Sun, we see it as it was 8 minutes ago. But when we observe a blazar located 5 billion light years away, we are seeing a signal that began traveling toward Earth 5 billion years ago. At that time, the Earth itself looked very different. Life on our planet consisted mostly of simple organisms living in ancient oceans. Complex animals had not yet evolved. Yet even then, the distant galaxy containing the blazar was already producing enormous jets of energy. These jets have been traveling through the universe for billions of years before finally reaching our telescopes. This makes blazars incredibly valuable to scientists. Because their light crosses enormous distances, it carries information about everything it encounters along the way. As the light travels across intergalactic space, it passes through clouds of gas, cosmic dust, and invisible magnetic fields. Each of these structures leaves subtle fingerprints on the radiation. By studying these changes, astronomers can learn about regions of space that would otherwise remain invisible. In this way, blazars act almost like cosmic flashlights shining through the universe. Their beams illuminate the vast emptiness between galaxies. They help scientists map the distribution of matter across the cosmos. They even help researchers study the faint radiation left behind by the Big Bang. This ancient radiation, known as the cosmic background light, fills the universe. When gamma rays from distant blazars travel across space, they sometimes interact with this background radiation. These interactions slightly reduce the energy of the gamma rays before they reach Earth. By measuring these changes, astronomers can estimate how much background radiation exists across the universe. This allows scientists to reconstruct the history of star formation over billions of years. In other words, blazars do not just reveal information about black holes. They also provide clues about how galaxies formed and evolved. Some of the most distant blazars discovered so far are located more than 12 billion light-years away. Observing such distant objects is remarkable. It means astronomers are seeing galaxies as they existed, when the universe itself was still young. At that time, galaxies were smaller, more chaotic, and filled with enormous clouds of gas. Supermassive black holes were growing rapidly as they consumed surrounding matter. Some of these early galaxies became extremely active. Their black holes began producing powerful jets that turned them into blazars. Even across billions of years of cosmic expansion, these jets remain detectable today. Modern observatories like the Fermi Gamma Ray Space Telescope monitor the sky continuously, searching for high-energy signals from these distant sources. Each new detection adds another piece to the puzzle of how the universe evolved. And yet, despite all we have learned, blazars remain mysterious. Their brightness changes unpredictably. Their jets sometimes appear to twist or wobble over time. And their immense energy still challenges our understanding of how black holes interact with surrounding matter. But perhaps the most extraordinary aspect of blazars is the fact that their light has traveled across unimaginable distances just to reach us. Across billions of years. Across billions of light years of empty space, carrying with it a message from the distant past. A signal from the heart of a galaxy, where a supermassive black hole continues to launch one of the most powerful beams of energy in the universe, the most powerful particle. Accelerators in the universe. Among all the extraordinary phenomena in the cosmos, few are as extreme as the jets produced by a blazar. These jets are not simply streams of light. They are enormous rivers of high-energy particles, magnetic fields, and radiation launched from the region surrounding a supermassive black hole. Inside these jets, particles are accelerated to energies that are almost impossible to imagine. Electrons and protons move at speeds incredibly close to the speed of light. Their energy becomes so extreme that when they interact with magnetic fields or surrounding photons, they produce powerful bursts of radiation. This radiation spans the entire electromagnetic spectrum, radio waves travel outward across intergalactic space. Visible light allows telescopes to detect the distant galaxy. X-rays reveal regions where particles reach extremely high temperatures. And the most powerful emissions of all appear as gamma rays. Gamma rays are the highest energy form of light known in the universe. They carry enormous amounts of energy compared to ordinary visible light. Some gamma rays emitted by blazars contain billions of times more energy than photons of visible light. Detecting these signals requires specialized space telescopes designed to observe extremely energetic radiation. One of the most important instruments studying these objects today is the Fermi Gamma Ray Space Telescope. Orbiting high above Earth's atmosphere, this telescope constantly scans the sky for bursts of gamma radiation coming from distant cosmic sources. Many of the brightest signals it detects originate from blazars scattered across the universe. When astronomers examine these gamma-ray emissions closely, they often observe sudden flares. A blazar that appears relatively calm one day can suddenly become hundreds of times brighter within a matter of hours. These sudden outbursts reveal something important about the physics occurring inside the jet. They suggest that violent shock waves may be traveling through the stream of particles. As faster streams of plasma collide with slower ones, enormous amounts of energy are released. These collisions accelerate particles to extreme energies, creating the intense radiation astronomers detect. In some ways, these jets behave like enormous versions of particle accelerators built on Earth. Scientists studying fundamental physics use machines such as the Large Hadron Collider to smash particles together at high speeds. These experiments reveal the fundamental structure of matter. But even the Large Hadron Collider is tiny compared to the natural accelerators found in blazars. The jets of blazars accelerate particles to energies millions of times greater than those produced in human laboratories. This makes them invaluable tools for studying extreme physics. By analyzing the radiation emitted by these jets, scientists can test theories about particle acceleration, magnetic fields, and the behavior of matter under conditions that cannot be recreated on Earth. Blazars may also play a role in producing some of the most mysterious particles ever detected. Across the Earth, detectors occasionally record extremely energetic particles known as cosmic rays. Some of these particles carry astonishing amounts of energy, far more than anything produced by stars or supernova explosions. For decades, scientists have searched for the sources of these ultra-high-energy cosmic rays. Many researchers now believe that blazars could be one of the main origins of these particles. The powerful magnetic fields and shock waves inside their jets may accelerate particles to energies far beyond anything else in the universe. These particles then escape the jet and travel across intergalactic space. Some of them eventually reach Earth, where they collide with molecules in our atmosphere and create showers of secondary particles. Although these cosmic rays originate billions of light-years away, their journey eventually ends high above our planet. Each detection provides scientists with clues about the violent environments where these particles were born. But despite decades of research, many questions remain unanswered. Exactly how are particles accelerated to such enormous energies? Why do some blazars produce stronger flares than others? How stable are these jets over millions of years? These mysteries continue to drive research in high-energy astrophysics. New telescopes and detectors are being developed to observe the universe with greater sensitivity than ever before. As scientists gather more data, they hope to uncover the mechanisms that allow black holes to launch such extraordinary cosmic beams. Because hidden within the jets of blazars lies one of the most powerful natural laboratories in the universe. A place where gravity, magnetism, and energy combine to create particle accelerators far beyond anything humanity has ever built. When blazars change in an instant, one of the most mysterious characteristics of a blazar is how quickly it can change. Most cosmic objects evolve slowly. Stars burn for millions or billions of years, and galaxies take enormous spans of time to grow and transform. But blazars behave very differently. Their brightness can change dramatically within hours, days, or even minutes. Astronomers observing these distant galaxies sometimes see sudden bursts of radiation known as flares. A blazar that appears relatively quiet one night can suddenly become hundreds of times brighter the next. These bursts are not small events. During powerful flares, the energy released by the jet can rival the combined brightness of entire galaxies. Yet the region producing this energy may be no larger than our own solar system. This rapid variability provides scientists with an important clue about what is happening near the central supermassive black hole. In astronomy, the speed at which an object changes brightness can reveal the size of the region producing that light. If a distant source brightens and fades within a single day, then the physical region generating the radiation cannot be larger than the distance light travels in one day. Otherwise, the changes would appear slower. For blazars, some flares occur so quickly that the energy must originate from regions incredibly small on cosmic scales. This means enormous amounts of energy are being released in areas that are tiny compared to the galaxy surrounding them. Scientists believe several processes may be responsible for these sudden bursts. One possibility involves shock waves traveling through the jet. The jet itself is not a smooth flow of particles. Instead, it behaves more like a turbulent river of plasma. Faster streams of particles may collide with slower regions ahead of them. When this happens, shock waves form inside the jet, compressing magnetic fields and accelerating particles to extremely high energies. These accelerated particles then emit powerful radiation across the electromagnetic spectrum. Another possibility involves magnetic reconnection. Inside the jet, magnetic fields are constantly twisting and interacting with each other. Sometimes, these magnetic field lines suddenly snap and reconnect in new configurations. This process releases enormous bursts of energy, similar to the solar flares that occur on the surface of our sun. But near a supermassive black hole, these events are far more powerful. The resulting explosions of energy can produce intense gamma-ray flares detectable across billions of light-years. One famous example occurred in the Blazar 3C279. Astronomers observed a sudden flare where the brightness of the jet increased dramatically within only a few hours. The amount of energy released during this event was astonishing. For a short time, the jet produced more energy than trillions of stars. And yet this entire outburst originated from a region smaller than our solar system. Observations like this challenge existing theories about how jets function. Traditional models suggested that the radiation from blazars should vary slowly because the jets themselves are enormous structures stretching across thousands or even millions of light years. But these rapid flares show that the most energetic processes occur extremely close to the black hole, deep within the central engine of the galaxy. To better understand these events, astronomers monitor blazars continuously using networks of telescopes around the world. Radio observatories track the movement of particles along the jet. Optical telescopes measure changes in brightness. X-ray satellites study high-energy emissions from near the black hole. And gamma-ray observatories search for powerful bursts of radiation traveling across the universe. By combining observations across different wavelengths, scientists can reconstruct the sequence of events occurring inside the jet. Each flare provides valuable clues about how energy flows through these extreme cosmic engines. Yet even with modern technology, blazars remain unpredictable. Some remain quiet for months or years before suddenly erupting. Others flare repeatedly with dramatic bursts of energy. And occasionally, a blazar produces an explosion so powerful that it becomes one of the brightest sources in the entire gamma-ray sky. These sudden changes remind astronomers that blazars are not stable objects. They are dynamic, violent environments shaped by gravity, magnetism, and extreme energy. Deep within the heart of distant galaxies, supermassive black holes continue to launch powerful jets that flicker and flare across billions of light years, signals from cosmic engines that remain among the most powerful and unpredictable phenomena in the universe. How blazars shape entire galaxies. While a blazar appears to us as a bright and distant source of radiation, its true influence extends far beyond the narrow beam of energy we observe. These powerful objects are not only spectacular cosmic phenomena, they may also play a crucial role in shaping the evolution of entire galaxies. At the heart of every blazar lies a supermassive black hole, with a mass millions or even billions of times greater than our Sun. When large amounts of matter fall toward this black hole, the energy released can influence vast regions of space surrounding the galaxy. The relativistic jets produced by the black hole carry enormous amounts of energy far beyond the galactic center. These jets can travel across hundreds of thousands or even millions of light years, pushing through clouds of gas and dust that surround the galaxy. As the jet moves outward, it interacts with the interstellar medium, the gas that fills the space between stars. This interaction can have dramatic consequences. In some cases, the powerful radiation and shock waves produced by the jet heat the surrounding gas so strongly that it prevents new stars from forming. Star formation requires cold, dense clouds of gas to collapse under gravity. But when a jet injects large amounts of energy into these clouds, the gas becomes too hot and dispersed to form new stars. In this way, the activity of the black hole can slow or even stop the birth of future stars in its galaxy. Astronomers refer to this process as galactic feedback. It is one of the key mechanisms believed to regulate how galaxies grow and evolve. Without this feedback, galaxies might continue forming stars at extremely high rates. But observations show that many large galaxies eventually slow down their star formation dramatically. Blazars and other active galaxies may be responsible for this change. By injecting energy into their surroundings, they prevent galaxies from growing too quickly. In other situations, the jet may have the opposite effect. When the powerful stream of particles collides with distant clouds of gas, it can compress those clouds, triggering the formation of new stars. This means that the same jet capable of suppressing star formation in one region may ignite star formation in another. The result is a complex interaction between black holes and the galaxies that host them. Over billions of years, this relationship may shape the structure of entire galaxies. Even our own galaxy contains a Sagittarius A star, although it is currently much quieter than the engines powering blazars. Evidence suggests that in the distant past, Sagittarius A star may have been far more active. Observations of enormous structures known as the Fermi bubbles, giant clouds of high-energy particles extending above and below the Milky Way, hint that our galaxy may once have experienced powerful outflows from its central black hole. These ancient eruptions could have influenced the structure of gas within our galaxy. By studying blazars in distant galaxies, astronomers gain insight into how similar processes might have shaped the Milky Way long ago. Blazars, therefore, represent more than just powerful cosmic beams. They are signs of an ongoing interaction between black holes and the galaxies that surround them. This interaction may determine how galaxies evolve, how stars form, and how matter is distributed across the universe. In the distant past, when the universe was younger and galaxies were filled with abundant gas, many more galaxies may have hosted active black holes, producing enormous jets. Some of those galaxies likely appeared as blazars from our perspective. Today, we observe only a fraction of these cosmic engines still active, but their impact remains written into the large-scale structure of the universe. Every jet launched by a supermassive black hole carries energy capable of reshaping its environment across unimaginable distances. And as long as matter continues to fall toward these black holes, the universe will continue producing some of the most powerful beams of energy ever known, the extraordinary cosmic engines we call blazars. Could a blazar ever threaten Earth? When people first learn about blazar, a natural question often follows. If these cosmic jets are so powerful, could one ever be dangerous to Earth? To answer this question, we must first understand the enormous distances involved. Most known blazars lie millions or billions of light-years away from our planet. Even though their jets contain incredible amounts of energy, that energy spreads out as it travels across the universe. By the time the radiation reaches Earth, it is far too weak to cause any harm. In fact, the signals we detect from blazars are so faint that they can only be measured using sensitive scientific instruments. But in theory, if a similar object existed much closer to our planet, the situation might be very different. At the center of a blazar sits a supermassive black hole that is launching a narrow beam of high-energy particles and radiation. Inside this jet are powerful gamma rays, some of the most energetic photons in the universe. Gamma rays carry far more energy than visible light. If a strong gamma ray beam were directed toward a nearby planet, it could interact with the planet's atmosphere in significant ways. One possible effect would be damage to the planet's protective ozone layer. The ozone layer absorbs much of the harmful ultraviolet radiation produced by stars. If gamma rays destroyed large portions of this protective shield, ultraviolet radiation could reach the planet's surface more easily. Over long periods of time, this could harm living organisms and alter ecosystems. Scientists studying the history of Earth have even considered whether powerful cosmic events might have influenced some ancient extinction events. However, when it comes to blazars specifically, the risk to Earth is extremely small. For a blazar to threaten our planet, several unlikely conditions would need to occur. First, a galaxy with an active supermassive black hole would need to be relatively close, within a few thousand light years. Second, the jet produced by that black hole would need to be aimed directly at Earth. Third, the jet would need to remain stable for thousands of years while its radiation traveled toward our planet. The probability of all these conditions occurring simultaneously is incredibly low. In our own Milky Way, the central black hole known as Sagittarius A star is currently very quiet. It is not producing the kind of powerful relativistic jets that define blazars, even if Sagittarius A star became more active in the distant future. There is no evidence suggesting it would produce a jet aimed toward Earth. Most galaxies with active jets are also located extremely far away. Astronomers have surveyed thousands of active galaxies across the observable universe, and none of them present any danger to our planet. So, while blazars are among the most energetic and violent objects in the cosmos, they remain fascinating subjects of study rather than cosmic threats. Instead of danger, they provide scientists with valuable opportunities to explore extreme physics. By studying how blazars emit radiation, astronomers can better understand how particles are accelerated to enormous energies. They can investigate how black holes interact with surrounding matter, and they can learn how these powerful jets influence the galaxies that produce them. In many ways, blazars serve as natural laboratories for studying the most extreme conditions in the universe. They allow scientists to observe phenomena that cannot be recreated on Earth. The same powerful forces that launch these incredible jets also reveal the fundamental laws that govern the cosmos. And although these distant cosmic engines may appear frightening at first glance, they ultimately remind us of something extraordinary. Across the vast darkness of space, the universe continues to produce structures of incredible power and complexity. Blazars are simply one of the most dramatic examples of that cosmic creativity. The future of blazars and the fate of their jets. Across the vast expanse of the universe, the powerful engines we call blazar will not remain active forever. Although these cosmic beams can shine with extraordinary brightness, they are ultimately powered by a limited resource, the supply of matter falling into the central supermassive black hole. As long as gas, dust, and stars continue drifting toward the black hole, the accretion disk will remain active. The swirling material will keep generating enormous amounts of energy, and the relativistic jets will continue blasting outward into space. But the universe is constantly evolving. Over millions or billions of years, the amount of available matter near the galactic center may gradually decrease. The intense radiation and powerful jets produced by the black hole can push surrounding gas away from the central region. slowly starving the black hole of the material it needs to remain active. When the supply of matter becomes too small, the accretion disk begins to fade. As the disk cools and thins, the magnetic fields that power the jets weaken. Eventually, the enormous cosmic beam that once defined the blazar begins to disappear. What remains is simply a galaxy with a quiet, supermassive black hole at its center. This transformation can take millions of years. During this time, the galaxy may pass through several stages of activity. It may first appear as a bright, active galaxy, with powerful jets extending outward across space. Later, the jets may weaken and shrink. Eventually, the galaxy may appear almost ordinary again, with only faint traces of past activity remaining. Astronomers believe that many galaxies may pass through these active phases multiple times throughout their history. Galaxy collisions, for example, can deliver enormous amounts of gas toward galactic centers. When two galaxies merge, their gravitational forces disturb the gas and dust inside them, sending huge streams of material towards the central black holes. This sudden supply of matter can reignite the accretion disk and trigger another period of powerful jet activity. In this way, a quiet galaxy can suddenly transform into a bright, active galaxy, and in rare cases, into a blazar if one of its jets happens to point toward Earth. Over billions of years, these cycles of activity and quiet periods may shape the evolution of galaxies across the universe. Even after the central engine shuts down, the enormous jets produced by the blazar may continue traveling through space for millions of years. The particles within the jet carry tremendous momentum. As the jet pushes through intergalactic space, it can inflate massive structures known as radio lobes. These lobes are enormous clouds of energetic particles that glow faintly in radio wavelengths. Some radio lobes stretch across distances greater than the galaxies that created them. They represent the lingering footprints of ancient cosmic jets. Long after the central black hole becomes quiet, these enormous structures remain visible as evidence of past activity. Studying these remnants helps astronomers reconstruct the history of galaxies. By observing the size and structure of radio lobes, scientists can estimate how powerful the original jet was and how long it remained active. These observations also reveal how jets interact with the gas that fills the vast spaces between galaxies. Sometimes the jets carve enormous cavities in surrounding gas clouds. Other times they trigger waves of compression that travel across intergalactic space. Over long periods of time, these interactions can influence the distribution of matter across galaxy clusters. This means that the activity of a single supermassive black hole can affect regions of space millions of light years across. Blazars, therefore, represent far more than just bright points of light in the sky. They are engines capable of shaping cosmic environments on enormous scales. But even the most powerful jets cannot last forever. Eventually, the universe itself will continue evolving. Galaxies will merge, stars will burn out, and the supply of fresh material feeding supermassive black holes will slowly diminish. In the distant future, active galaxies like blazars may become far less common. The universe may gradually enter a quieter era, where black holes remain mostly dormant and cosmic jets fade into history. Yet for now, blazars continue to shine across the universe. Their beams of radiation travel across billions of light years, carrying with them information about the extreme environments surrounding supermassive black holes. Each photon that reaches our telescopes is a messenger from the distant past, a signal that began its journey long before our civilization existed. And by studying these distant signals, astronomers continue to unlock the secrets of the powerful forces shaping the cosmos. Because somewhere in the darkness of space, countless galaxies still harbor these extraordinary engines, launching enormous jets of energy that illuminate the universe in ways we are only beginning to understand.